Serge, for this amazing introduction. Now I have to keep to that. I'm not sure I will be able to do that. Great. So it's my pleasure here to be today, and I wanted to I guess introduce who I am, just in case you guys don't know. So I have 3 jobs, which keeps me quite busy. I am still an academic. 1 day a week, I am in the University of Toronto. And the Vector Institute, which I co-found with a whole bunch of people that you see in the picture, including Jeff Hinton. And the greatest news, I guess, as of May 1st, I'm also heading a new lab of Uber ATG in Toronto. So self-driving cars are in Canada now, and that's really, really exciting. So today, I'm going to talk about what led to the Uber acquisition, but not what happens after May 1st. Okay, so bear in mind that. So I guess perhaps we have already seen a lot of discussion about why we need self-driving cars. But what is very important for me is actually that, we need to lower the risk of accidents, but we need to provide mobility for many people that right now cannot go to the place they want to go. And we need to think of the future of public transportation or ride sharing, right? And in particular, we need to share resources. And this is really the picture of our cars. And that shouldn't be like that, right? 95% of the time, the car is parked, right? So we are just utilizing our planet without real reason. So if we look at typically what is done in, I guess, self-driving car companies, so the stack is typically based on things that came out of the DARPA challenge. And these systems are pretty good at localization, path planning, obstacle avoidance. And there is 2 things that they do which actually made them not super scalable. The first thing is to use the LiDAR, right? So although prices are dropping, it's still quite expensive, right, to buy a decent LiDAR. And the other thing, which is the beast in the closet, is actually mapping, right? So just to map the US, it's estimated that it's going to take $2 billion, right? So that we can scale to, say, all Uber markets like that. So what I've been working on for the past 7 years is how to make solutions that are scalable, meaning that chip sensors and try to drive without maps or with as little prior knowledge as possible. Now, if we want to do something of this form, we need to think about many different things at once. The first thing that as an academic was difficult was actually data. And so we created many years ago, I guess, still the only benchmark for self-driving and computer vision, which is Kitty. And to my despair, it's still the only benchmark, which I don't understand. The other thing that is important is learning, right? So we can't just handcraft everything because we need to be robust to scenarios that we have never seen before. We need holistic models that reason about many things. At the end of the day, we have fixed computation for many things, many tasks, and we need to think of hardware at the same time. All right, so if we want to get rid of the LiDAR, get rid of the maps, what are the things that we need to do? So everything I'm going to show you today is mostly deep learning. Okay, so I don't need to say that. But this is typically what you can do. And with deep learning, and basically you have robust, good, and fast stereo reconstruction. This can run real time, and up to 40 meters can basically almost replace the LiDAR. Other things that you need to do is that you need to do perception. So I spent the past 1.5 years obsessed with instance segmentation. This is what you're seeing here in the image. So the idea is you have a single image, and you're interested in labeling every pixel, but not just with the category of say, car, road, but also you want to estimate this is one car, this is another car, etc. And this is a particularly difficult problem for deep learning because the loss function is agnostic to permutation. So we built some interesting technology lately based on the watershed transform that actually scales really well. It's independent of the number of objects, so you can run real time for any scene. And this is strong generalization. It's trained in a set of cities and tested in another set of cities. You see the prediction in the middle and the ground truth on the right. Okay, so even with crowded scenes, can actually do pretty well. Now, if you want to do self-driving, just labeling pixels is not going to get you there, right? So you need to really estimate what's happening everywhere in the scene. This is our latest, greatest results. This is joint detection and tracking. So this is actually quite technically very interesting. You can backpropagate through solvers. And here you see the results of what we have as well. And in general, what you want to do is estimate everything that is in the scene. So here are some results that we had even a couple of years ago with just having a single camera mounted on top of the car. The car is driving in intersections it has never seen before, and is able to estimate the local map of the intersection. So it's creating the map on the fly. It's estimating where the ego car is. So it's doing localization as well as estimating where every car is in the scene and the traffic situation that you see on the bottom left, even though it doesn't see traffic signals or things like that. So the cars are color-coded by their intention. So basically here we are estimating where everybody is going and what is going to be going in the next couple of seconds. And this is, as I said, single camera, new scenarios that we haven't trained on. Other things that you need to do is actually localization. So localization is an interesting problem because typically the way it's done is that, say Waymo does it, is that you go around and then you collect how the world looks like, and that's really expensive, meaning that what it means is that basically you need to know the appearance of the world at every point in time, right? So here what we look at is just by using OpenStreetMaps, which is this cartographic map of the environment and the motion of the vehicle, we can estimate really quickly where the vehicle is in the global coordinate system. Okay, so you see here, so you have a probability distribution over the graph of the road. The vehicle starts driving. You have a few months of the distribution, and very quickly, right, we know exactly where this vehicle is. Right, so this is a Manhattan-like scenario. So there is 2 modes of the distribution, but again, soon we're going to do something where there is only a single location. And this, for the whole city of Karlsruhe, which is 2,000 kilometers of road, it takes 35 seconds of driving to actually localize with precision of 2 meters, which is the precision of the maps that we use. These maps, OSM, they're available for free online for 60% of the world. So you can just download. You don't need to capture anything. It's free. Now, in terms of mapping, right? So why do car companies or self-driving car players use maps? You can think of a map as a sensor, which basically tells you the static part of the scene, right? So it gives you robustness, and it allows you to only look at the dynamic objects. So the problem of the way that mapping is done is that you have, say, one of these cars, right, with these expensive sensors, and basically you drive around the world, you capture data, and then there is some labeling process where you basically say, okay, where are the roads, where are the lanes, where are the possible places where you can park, etc. Okay, so that makes you have very small coverage because it's at the vehicle level and it's very expensive, right? And as an academic, I look at, can we actually do this by spending $0? Okay, and so it turns out that you can use aerial images or satellite images. Satellites pass around the Earth twice a day, so you have this up-to-date view of the world. And we create methods that can automatically extract the HD maps of the form that you see on the top, where you have lanes, parking spots, sidewalks, etc. Just automatically, and it takes only 3 seconds in a single computer to estimate this per kilometer of road. Okay, so basically, with a very small cluster of say 10 computers, you can run the whole world. Okay, and have up-to-date estimates. And one of the things that, a long time ago I created Kitty, right? That was, I guess, 5.5 years ago, something like that. And one thing that it bugged me about mapping is that it's only the players, the companies that are actually working on this. So I created Toronto City. This is about to go online soon, where basically we have, for the Greater Toronto Area, all possible views of the city. So the GTA, the Greater Toronto Area, is 20% of the population of Canada. It's huge. Okay, and we have all these different views, so panoramas, LiDAR, cameras from aerial views, drones, etc. Now, as an academic, I cannot label, I cannot pay labelers to label all this, right? Just for the aerial images, it's going to cost between $20 to $30 million to label that. Okay, so what I did is I went to the government and I got all this information from maps that the government have captured, that are 3D maps of the city, every single building, etc. And then basically we develop algorithms that can align all the sources of information, including all the different sources of imagery, as well as the maps, and can create automatically ground truth. And here you see the quality of the ground truth is really, really good. Okay, so as a consequence now, we have ground truth for the whole Greater Toronto area, and we're going to put online the benchmark very soon. So these are just the tasks that you can participate, doing instance segmentation, doing semantic segmentation, doing all this stuff. Other things that we have built since then is we also build deep learning techniques to actually be able to extract these maps automatically, and this is what you're seeing here for. I guess my video is stuck somehow. Yeah, you can see from aerial images, and one of the things that was interesting is that from panoramas, you can actually get automatically centimeter accurate maps. That was actually quite interesting. All right, so just to conclude, I've shown you a couple of things that my group has been building in the last 7 years on how to make affordable self-driving cars at scale with sensing, perception, localization, and mapping, and the next big benchmark, and there is so many things to do. And I hope to start a new episode of my life, I guess, at Uber and building really things at the scale. And whoever is interested in joining, please come and talk to me. Thank you.